Hello, everyone. My name is Haiming Liu. I'm now working as a research associate with Metal Earth project at Laurentian University. The title of my presentation is applying different machine learning techniques for constructing the data integration models in the Larder Lake area in Northern Ontario. And today I'm going to show the preliminary result for the data integration modeling DM work and evaluation of our models. And another work is to investigate the geocore data, geochemistry data using the machine learning techniques, especially the ensemble-based classifiers. And in general, we know that machine learning algorithms can be classified as unsupervised and supervised learning algorithms. And unsupervised algorithms can be used to reduce the high-dimensional data and cluster the data. And supervised learning techniques can be used to classify the data set and make predictions. In this study, we use the principal component analysis and the k-means as the unsupervised method to investigate the variable correlations. And the random forest as a very powerful supervised tool to classify the data and make predictions. And we can also use random forest as the point shows that we generate the mineral potential maps. And the partial least square discriminant analysis as another supervised classification method. We use that to build the discriminant models and investigate the contributions of the variables for classification. And so in this study, we combine several machine learning techniques to explore the insight that are hidden in the data. And here is the workflow for our study. The input data set includes like the geochemical data set, geophysical data, and also the geological data, such as the lithology and the structure. And for missing data and the data below the detection limit, we use the imputation method to make a complete data set. And also, we ran the PCA and the k-means for the data to reduce the high-dimensional data. And we use random forest to construct the classification model, and we selected the non-deposit locations and randomly select the non-deposit locations as a training data set. Then the mean probability maps on the pixel-to-pixel basis are generated as the output maps. And this map view shows the high potential and the low potential areas for gold mineralization. And in addition, we ran the plus DA, the partial least square discriminant analysis to investigate the geochemical data associated with the geophysical classifications. And this view shows the geophysical properties of mineralized rocks from a regional scale. And to visualize the data, the result, we use the ArcGIS and the Leapfrog to show our result. And here is a geology map of the Larder Lake area. As we can see from the map that there are two major faults, the Larder Lake, Cardiac deformation zone and the linking-Nipsing shear zones in the south. And along the mafic and the ultramafic deformation segment, and there are considerable gold deposits that are associated along this this incompetitive like the ultramafic mafic rocks. And in the contrast, there are also the mafic to felsic intrusions along the linking-Nipsing shear zone, and we associate, and this intrusion is associated with the gold mineralization events. In this study, we choose the largest gold deposits occur Artisan, Shermany, and the linking-Nipsing shear zones in the south. And also, we include the geochemical data that's compiled from the Ontario Geological Survey that as our geochemical data site. And here are the lithology. Here is the geology layers, such as we use the lithology contact. We use the multi-promixities to the lithology contact from the 50 to 200 meters. And we use the promixity to the northern eastern trending fault and the northern western trending fault that has the promixities to within the 1 kilometers. And the geophysical data provided from the Mustafa that we include like the density, susceptibility, resistivity from the depth of minus 750 meters to minus 6,750 meters underground. And we ran the k-means, for clustering and the whole data set. But we classify the data other than 4 clusters, we use 3 clusters just to show like this is resistivity and the susceptibility, and the 3 clusters, such as the cluster 1 is the high resistivity and the low susceptibility, and the cluster 2 is low to high resistivity and the high susceptibility, and the cluster 3 is low to middle resistivity and the low susceptibility. And here also we visualize the cluster result on the map. And for the geochemical data site, we run the PCA plot, we run the PCA analysis to investigate the structure of the data. And from the first and the second principal component biplot, we can see that they capture the major variety of the data site. And we can see that the gold, arsenic, antimony that are associated with nickel, cobalt, and chromium, which indicating that these gold mineralization are associated with mafic to ultramafic rocks. And also the relative contribution of variables shows that from the PC1 to PC4, that gold has relatively high contributions. And the PC8 also shows the high contributions. So we include PC1 to PC4 and PC8. And here is the geochemical data layers that we use to generate our models. We use the PC1, principal component 1, PC2, PC3, PC4, and PC8 to as the input of our geochemical data, because the sample distribution is highly biased. So we use the inverse distance weighted interpolation to overcome the unbalanced sample distribution issues. Here is a major result of our data integration models, and 32 layers, including the geochemical, geophysical, and geological data set we used. And we use 127 gold deposits and 10 sites of the randomly selected 129 points as non-deposit locations. And we use 2/3 of the data as a training data site, 1/3 of the data as the validation data. We repeated the random forest model for 10 times and calculate the mean probability value to generate the classification map. The locations that on the map indicating that the locations with a higher probability values indicates a higher potential for gold mineralization. And these hot zones, such as here, that are also considered with the locations of the known deposit locations. And another output of the model is importance values for each predictor. From this plot, we can see that the principal 3 and the principal 8, and together with the lithology contact, shows very high importance. And for this research area, and however, the geophysical clusters such as class 3 and class 2 are the least important predictors. And that's why we need to look at the PC3 and the PC8. What are they look like? Here, if we look at the principal component biplot for PC3 and PC8, we can see that the gold, iron, copper, arsenic, they are highly positively correlated together with negative PC3, PC8. And these samples are mainly the gold-rich samples. Whereas on the opposite side of the biplot, we can see that they are tellurium, some of the silica, and these are the gold poor samples. And here, if we look at the negative then if we also we can see that tungsten, sulfur, and titanium are positively correlated. So the PC3 that can be plays very important role to distinguish the strong mineralized rocks from the weak mineralized rocks. To evaluate the performance of our model, that we generate several plots, such as we can use the mean accuracy of the 10 repeated random forest model, that we got the 95.6% of the accuracy. And also we can see that from the success rate of a classification plot, that the area under the curve for this classification is 95.9, and also shows the high efficiency of rate of the classification and the non-departed using the 32 layers. And also here we can use the ROC curve and the AOC under the area under the curve that also shows 96.1, also shows a very high efficiency. So in order to better understand our data integration model, that we use the partial least square discriminant analysis to investigate the relationships between the geophysical data clusters and the geochemical compositions. And the 3 clusters that we used, 3 clusters were identified based on the K-means clustering analysis of the geophysical data. And we appended them as attributes for the geochemical data. Then the geochemical signatures for each cluster can be identified. From the first and the second loading plot, we can see that the low to middle resistivity and the low susceptibility samples that they cluster together and form a cluster, form a subgroup. And because they have a relatively high values of gold, sulfur, and the tungsten, which indicate these are the gold-rich rocks. And from the score contribution plot, we can also see that the arsenic, we can also see that the arsenic here, and also for each group, arsenic and the tungsten and the gold show similar contributions to the low susceptibility group, whereas the tellurium show high contributions to the high susceptibility group. And this is consistent with the findings in the Canadian malartic deposit, that the low density and the susceptibility are always associated with the gold mineralization due to the hydrothermal alteration to break down the magnetite and release the iron. And from the variable importance on the projection plot, we also can see that the VIP larger values larger than 1, such as like tellurium, shows very high contributions, a very important signature that to divide these 3 groups. So we can carefully generate the conclusion that it is likely that the tellurium is much more sensitive to the change of the geophysical properties of the rocks. And another work we do is we use the data that we already have at a Kerr Artisan deposit to predict on some unknown informations on the Chamonix, because we already in the previous study we show the geochemical data site that these 2 deposits, they show quite a similar lithogeochemical data site. So let's look at the principal component analysis. From the previous investigation of the geochemical data using the PCA, we can conclude that the Kerr Artisan that using the GeoCore data, we have a 1,200 data set here, and they show quite a similar distribution of the samples and also the correlations of the element. So we can use the information from the Kerr Artisan to predict some of the information in Chamonix. This work that we can be realized through the ensemble-based classifies. And before several studies, they already proposed the ensemble classification using different classifiers, such as different machine learning algorithms. And we use our training data set as known data, and we input and make them like stacked together. And then we input the attribute from the known deposit to predict some of the labels in the unknown. And this study already realized has been applied to the GeoCore study from the GeoCore data to using the known geophysical properties and the geochemical data to predict some other information in the GeoCore for unknown deposit. And here is the machine learning workflow that here we can use the data from the Kerr Artisan that 80% of the training data set was used and 20% of the data as a validation. That we from the Kerr Artisan GeoCore data, we have the lithology, alteration assemblage, and we have the parasitic alteration grade and the sodic alteration grade. This known information can be used as an attribute that we can train our model. So the base learner that we use, like a k-means k nearest neighbor, random forest, and the artificial neural network, and support vector machine, naive Bayes, and the linear discriminant analysis and the classification trees, that we use these kind of learnings that they can produce the similar output as the input for next learner, such as the ensemble learner. And ensemble learner, we use 3 different ensemble learners. The first is the average. We use the random forest and our artificial neural network as the we calculate the mean probability as the training data. And also we input them as the random forest model to generate the random forest ensemble model and AN ensemble model. Then this kind of a workflow can predict the similar information for Chamonix deposit. So let's look at our result. This the lithology predictions that the deposit, we visualize the data that for the Chamonix deposit, we have 7,000 data that was unlabeled. But here we can see that we give them the lithology, and also we have the alteration assemblages, and also here is the potassic alteration grade, intensive potassic, and the non or weak potassic altered. And also we can also see the sodic alteration zones here that shows different grade. So we consider that this kind of work can show the target in the drill cores that can help the geologists to find, locate maybe the alteration zones for the ore body. And to evaluate our machine learning algorithms, we use the accuracy plot. We can compare different accuracies between of the different machine learning techniques. And also the RC curve can be used to show the efficiency of our classification or predictions, such as we can see that ensemble average always shows high of the accuracy and high AUC values in our study. So the major conclusions of our study is that we use geophysical and geochemical and the geological data for our data integration models that shows a high accuracy to predicting the mineral potentials. And the random forestry is a very useful tool to find the potential gold mineralization events. And also partial least square discriminant analysis can be used to extract the geochemical signatures based on different sub classification types. And the different machine learning tools can show high accuracy to predict the rocks or the alteration assemblage, which can help in the mineralization targeting. So thank you, everyone. That's my presentation.
Great, thanks very much, Haiming. We have time for a question. There is one. Bob, you got your hand up first.
Yeah, I'm curious. There have been numerous alteration and mass balance calculations done on these rocks, and the tellurium anomaly really intrigues me. How does your results compare to the previous mass balance work? Are there tellurium losses in those rocks that have been previously identified?
Yeah, so Bob, the preliminary result for our work just shows that tellurium is very sensitive to different subgroups of the geophysical data clustering, but we have no idea that if this kind of rock is rich in tellurium or they are poor in tellurium. So this model, this classifier just gave us an idea that tellurium may be very, they can divide it, they contribute most. So more work that we have to identify, maybe we have to go back to the geochemical data to see that if they are quietly rich in the tellurium or they are associated with other mineralization events. So that is my current study. We will focus on this.
That's it. The tellurium to me is really very interesting. So thank you.
Thank you.
Okay. Eric, do you have a question?
Yes, you go back to the prediction you did for Larder Lake, and you had a number of, I think you said 127 gold deposits. Now, are they really deposits or are they mineral occurrences? And in terms of deciding what constitutes a training set in terms of the mineralization, would it not be better to use just the producing gold mines or the past producers as the training set and let's see how those mineral occurrences end up predicting?
Yeah, so the training data set include different size of the I didn't divide it like developed mines or the closed mines or showings that I include all the information that with mineralization events. So probably we can divide it another data site, such as the showings and occurrence that can be used as a prediction. How our like classification map can perform in this kind of a purpose. So that is my next job, that I can show another like another area or the same area that we just divided another group to show that how efficient of our mineral potential map.
Right. Okay. All right. I just thought I'd point that out. I'm just not sure it's useful to use all the mineral occurrences in the training set. So
yeah.
Thanks.
Thank you, Eric.
All right.
I just have a comment, if that's okay, Ross.
Yeah, go ahead.
Yeah, just in following on with Eric's concerns, one of the problems with past producers and present producers is that in many cases there's just not enough of the training sites to make a valuable prediction with random forests. So we have to be a bit careful when it comes to that. And certainly some of the work I did in Red Lake, what I did, Eric, was look at producing a map based on just the past producers and producers, and then compare how well that predicts the occurrences and vice versa. And that seemed to work out fairly well. So those are just some ideas that Haiming may want to entertain in his next go around. So
yeah, and I think there might be some iteration required there in terms of finding a suitable training set. So yeah, it's certainly not a trivial thing to do.
No, it isn't. And one of the other problems is that's being researched now with random forests and digital integration models or mineral potential maps, whatever you want to call them, is the looking at how we define random points. Do we just make them random over the area, or as Paran has done, make them random over the area, but make sure it's a certain distance away from the known deposit? So that is ongoing research that we have to entertain and continue as we go along. So
yeah, some simulations might be useful there, where you try a range of different training sets, or let's say the deposits that are not known or are just showings.
Sure.
And run many simulations and just see what kind of average results you get on that.
Sure, that's not a bad idea.
Okay, Josh, if you have a quick question, we can take it.
Yeah, thanks, Ross. Good presentation, Haiming.
Thank you, Josh.
Just a quick comment to emphasize Eric's point. I think it's even worse, because the challenge really is that there's one deposit on that map area that is of a sufficient threshold that most explorers would be looking for. So from an exploration point of view, and this is really, I think, one of the crux of one of the main challenges of bridging these machine learning techniques and then making them applicable in practice. And that's there's a very large, there's probably a greater difference between a world-class deposit like Care Addison and one of the smaller past producers than there is, that's a similar sized leap than between even the past producers and the occurrences. And these things are very rare. So that's, it's very difficult to find examples to train on, of course. So I think most people know this, but I thought I'd just emphasize it again.
Yeah. So yeah, this is not very easy to find a similar like a stereo area like us. But one thing is that we can divide it, the training data set for the in one deposit, we understand one drill core or several drill cores well studied, and then predict several the non-studied drill cores. That would be a very interesting idea, I think, for one deposit for exploration purpose.